Planet Earth is around 4,500 million years old. After the Big Bang that created the universe, lumps of boiling debris collided, cooled and gelled together to form a bald, rocky, erupting planet. It was bombarded by comets and meteorites and held by gravity in orbit around the Sun. The Sun's surface temperature is around 6,000 degrees Celsius. At 92 million miles away, this means that primitive Earth, once cooled, must have started off life with an average surface temperature of around minus 15 degrees Celsius, which swung wildly from day to night. The atmosphere was started by eruptions from the fiery interior of the Earth, which gave off gases held by gravity. Volcanoes still throw up this primitive atmosphere of water vapor, carbon dioxide, sulfur dioxide, and small amounts of nitrogen too. This primitive atmosphere was rich in the greenhouse gas, carbon dioxide. This is how the average temperature of Earth came to rise above freezing to 15 degrees Celsius where it is today. A runaway greenhouse effect like that on Venus was stopped by the water steam bursting out of the volcanoes and forming huge rain clouds. These washed out much of the carbon dioxide in the atmosphere and formed the oceans, and today the carbon can be found at the ocean bed. The oceans blocked out harmful ultraviolet sunlight, so primitive life began in the oceans. The living cells fed on the carbon and gave off oxygen as waste. Over millions of years, oxygen floated up from the oceans and up into the stratosphere to react with sunlight and form ozone. Once the ozone shield was thick enough to ward off the lethal ultraviolet rays, life moved out of the water's edge and onto the land. This changed the planet's surface from bald and reflective to dark and absorbing. This stopped the wild swing of temperature from day to night. Climate and life on Earth had become vitally linked. This modern climate began some 500 million years ago. Since then there have been small, periodic climate changes. We call them ice ages. Over thousands of years, the Earth has had a very slow periodic wobble, tilt and spin. It is so small it's hardly noticeable, but it causes the average surface temperature to change by some 4 degrees Celsius across the globe. Although this does not sound very much, it was in fact enough to reverse the last ice age 10,000 years ago, clearing ice from London, from Paris and from Chicago back to the pole. Today we're between ice ages. The next one is due within 1,000 years, when permanent ice may well form as far south as the Tarns of Wales and stay for 100,000 years. Throughout history, the climate and the weather has mystified mankind. In the past, people have worshipped weather gods and handed folklore down the generations. However, weather lore is fundamentally flawed, and with the invention of the barometer in 1643, old wives' tales gave way to science. The science of weather slowly became accepted, and in 1854, Parliament voted to set up a department to collect weather observations. During the debate, one MP expressed the hope that in years to come we might know the weather 24 hours in advance. This caused a great deal of laughter. In 1859, a fine new vessel, the Royal Charter, was sunk in a storm, killing 500 people. As a direct consequence, the department was granted a bigger budget and became the nation's storm warning centre. The first storm warning was issued in 1861, and the first routine weather forecast was given in 1862. The Met Office and weather forecasting were born. Hello, it's just coming up to about 7 o'clock in the morning, and I'm just going to do the first weather forecast from the BBC studios here in London. Many people, of course, want to know what the weather's going to do each day. They don't have an interest in meteorology per se, but they like to hear the weather. It is a fascinating subject, and that's what I'm going to be telling you about later on in this film.
Stand by, going on the air.
Good morning. Well, at last we got rid of that really lovely fine spell of weather, so we can all go back to work, comforted in the thought that we're not missing out on anything. It's become much more mobile now, the weather across the Atlantic. There's all sorts of things coming down, particularly from the northwest. There's a depression that's brewing south of Iceland. It's on its way to Scotland, and it's going to cover us, most of us anyway, with cloud, and there'll be rain. Meteorology is the science, the study of the atmosphere. The state of the atmosphere outside, we call that the weather. The average weather over the years, we call that the climate. Each morning on TV we can watch the weather over thousands of miles of land and sea. By comparison, if you go out and look from a good vantage point, your horizon would be no more than 10 miles away. Now, to forecast the weather 2 or 3 days ahead, we need to know what the weather is doing right around the world. You see, weather is deterministic. That is, what the weather will do depends on what the weather is doing. The troposphere, that's the lowest 10 kilometers of atmosphere which holds all the moisture, the weather sphere, it's in constant turbulent motion. To predict its future motions, we need a model that mimics its behavior. If the model is well thought out and the observations we feed it are accurate, it should show us what the weather will do. However, to make a good model, we must first understand exactly how the weather works. The seasons are caused by the tilt of the Earth's axis relative to its plane of orbit around the Sun. The hemisphere that's tilted towards the Sun has summer, and at the opposite end of the orbit, half a year later, it becomes winter. The Sun's heat is much more intense at the equator than at the poles. Consequently, hot air rises at the equator and sets off poleward. Cold air over the poles, meanwhile, sinks and sets off equatorward. If nothing else were to happen, a circulation from equator to pole would result, and in fact we'd have a northerly wind over Britain. However, since the Earth does rotate, the circulation breaks into 3 distinct overturning cells. And where the warm air plate overlaps the cold air plate, there are sharp temperature differences, and this is where jet streams are made. Jet streams are high altitude, fast currents of wind. Because of mountain ranges that stick up into the atmosphere and obstruct the flow, jet streams actually track a changing, wiggly path around both hemispheres from west to east. The north-south overturning cells that we saw before mean that the surface winds blow from north to south or south to north, except of course that the planet is rotating, and that deflects the winds. In the northern hemisphere the deflection is to the right, in the southern hemisphere the deflection is to the left. This deflection can be seen by imagining a turntable rotating. The pole is the middle, the equator is the rim. Firing from the pole, aiming at Britain, results in a miss to the right. This apparent deflection to the right is called the Coriolis force. So the general pattern of surface winds over the Earth produces great battles for territory, convergence, near 60 degrees latitude, making cloud and rain to be dragged around by the jet streams. Whereas near 30 degrees latitude, there's divergence. The pattern produces quiet, calm, doldrum weather. The climate then depends on the intensity of the sunshine, the prevailing low-level wind, the proximity of oceans and continents, and whether or not the air is battling for territory over you. If we look now at a slice of the planet, we can look at the combined effects in the air and in the sea. Across the Atlantic Ocean, the prevailing surface winds set up the Gulf Stream circulation, bringing us warm Caribbean waters. On average, this makes Britain the warmest place in the world between latitudes 50 and 60 degrees. The sun's excess heating at the equator and deficit at the poles sets the oceans in motion, a slow and lumbering circulation of ocean between pole and equator. As we've seen, the rotating planet breaks up the atmosphere into comparatively fast-moving transport cells and forms the jet streams. Over our latitudes, the battle for territory between warm and cold air develops low-pressure cells or depressions or storms, and they're steered towards us by the jet stream. And just how do these storms begin? You'll recall that to the north of Britain over the poles the air was sinking, and over the subtropics the air was sinking. High to low deflected to the right, high to low deflected to the right. This then is the battle zone over Britain. Which stream will win, the cold air from the north or the warm air from the south? If the cold air is winning, we say that the leading edge of the cold air, the polar front, is advancing. But typically, the warm air does bulge through in a few points, and at this point, the warm air, the light air, is alleviating the surface pressure. So if we were to draw lines of surface pressure, constant pressure, we find that the circulation looks like so, and this is a little area of low pressure known as a depression, and typically it approaches the British Isles like so. After a while, the cold air begins to overtake the warm air ahead of it, and where they overtake, we have what's called an occlusion. The warm air is lifted completely off the ground, and the cloud that's associated with this kind of warm sector depression looks something like that. So from satellite, we are looking for that sort of shape approaching the British Isles. And in fact, on this satellite sequence here, you can see that. Now, if we take a cross-section through this warm sector depression along this black line, calling that A and that point B, then the clouds from the side look like this. Point A is the leading edge of the surface warm air, that's the warm front. The air aloft, the warm air aloft, is riding up on the cold air ahead, and that uplift of air is causing a deep bank of cloud to form. The highest altitude cloud is the cirrus. The cirrus is miles ahead of the surface warm front at point A. Cirrus typically looks like wispy mare's tails high in the sky. Under the cirrus comes cirrocumulus. Cirrocumulus is high altitude, very white cloud, slightly fleecy, a sheen to it. Underneath that, cirrostratus, that looks like this, a thin veil of high ice cloud, producing hazy sunshine rather than direct strong sunshine. Beneath that is outer cumulus. Outer cumulus looks like this. It's more fleecy, more like a sheep's fleece. Very beautiful, makes splendid colours depending on the angle of the sun. Underneath that, outer stratus, it's a thickening veil of milky skies. This is when the sun fights a losing battle. Often it forms a halo round the sun. Lower still, nimbostratus. This is blackening, gloomy cloud. The skies look threatening and rain begins to fall. In the warm sector between A and B, there is stratocumulus. Stratocumulus is typically like this, pancakes or rolling clouds. They look sometimes like bubbles that can't quite grow high enough and then spread out. The low cloud of the warm sector, the drizzly cloud, stratus. That's low cloud that sits often on hills. Often fog lifts into low stratus, a sheet of grey. At the approach of B, the cold front, comes cumulonimbus. These are the deepest convective clouds in the atmosphere. Typically they have anvil tops, they produce thunderstorms, thunder and lightning. Often tornadoes come out of their underbellies. But following B, following the rain at the cold front, the sky's clear, and typically the skies are littered with cumulus. Cumulus look like these, those white fluffy bits that you often see in the sky. The battle for territory between warm and cold air is not the only way of producing clouds. On a hot afternoon, the thermals rise, and if the thermals rise high enough, expand and cool, so the thermal will be capped by a cloud, because the temperature has been reduced as thermal rises to its dew point, the temperature at which dew would form on the lawn, and the cloud base is at its condensation level. Another way of producing cloud is by having a hill that obstructs the flow, that forces the air up. The air is cooled to its dew point and forms a cloud at its condensation level. And why do you think the cloud has a higher cloud base on the lee side of the hill? We can see this effect on this piece of film here. It is this knowledge of how the weather works that we use as a basis for our model. To spot weather developments, the model needs a mass of information. The model is held in a supercomputer. Inside the computer, the surface of the world is represented by 1/3 of a million grid points, with 15 levels above that making a 3-dimensional net. This net of 5 million or so grid points is our model's atmosphere, the computer's own little universe. Each grid point is fed a reading of temperature, of pressure, of wind, and of humidity. So how do we go about collecting these 20 million pieces of information from all over the planet? Each land observation site has a Stevenson screen. This is a Stevenson screen. It's the home for thermometers to measure an assortment of things. There are a number of thermometers in here. You notice the door opens this way and the sun is behind the house, so we can't get direct sunshine in when I open the door. And in fact, it's louvered and painted highly reflective so that the air can pass through nicely and the sunlight's reflected away. So it's the shade air temperature that this ordinary thermometer measures. There's another similar thermometer with the complication that it's got a piece of muslin, a wet cloth, wrapped around its bottom. So it's called the wet bulb. We also have a maximum thermometer, a minimum thermometer. We have a chart that shows how the actual temperature has changed recently. It goes round with time. And the reason that we've got this wet cloth wrapped around the bulb of the thermometer is that the water evaporates from the bulb and therefore cools this thermometer more than the normal dry bulb thermometer. The rate at which water evaporates from this wet cloth depends on the humidity of the air. If the humidity is very low, if it's a fresh day, the water evaporates nicely, like washing on the line dries quickly. If it's a very humid day, absolutely damp and saturated, the water from this cloth hardly evaporates at all. Therefore, the two thermometers will read the same. So the difference between the two thermometers, the difference in their readings, is a way to tell you how humid it is. And that's worked out by a little device, and it's plotted on this chart. We have 60% humidity today. We have an air temperature of around 13 degrees, and we have a wet bulb temperature of around 9. So 13 minus 9 works out to a humidity of 60%. In very remote areas we have automatic weather stations, and for observations over the oceans we use ships and aircraft and ocean buoys. But we don't just need observations from the surface of the planet, we also need to know what's happening at different altitudes up through the troposphere. For example, measuring surface wind speed with an anemometer is straightforward enough. So many revolutions per second equals so many miles per hour. But to discover wind speed at altitude, we have to use a radiosonde. A radiosonde is a hydrogen-filled balloon released up through the atmosphere and tracked by radar. So the massive scale of the modern operation is now becoming apparent. Every day we must collect millions of vital bits of information like parts of a jigsaw. And of course, where would we be these days without radar and satellites?
The black blobs, they have the high liquid water content. They're the clouds that are likely to rain, and a radar scanner underneath all this cloud would have a strong reflection of its echo from that cloud and tell us that it's a rain cloud. But where has all this cloud come from? Is it developing? What's the weather like thousands of miles away upwind? Well, to remotely sense that, of course, we use satellites. Way above all this cloud, out in space, 22,000 odd miles in space, geostationary satellite called Meteosat, above the equator where the Greenwich Meridian crosses it, constantly looks at the Earth footprint, and because it's stationary with respect to us, the land and sea doesn't move, but what does move is the atmosphere, and of course the weather is a snapshot of the atmosphere in motion. Those snapshots from the satellite are sent to that dish behind me there, and that collects the data.
The images are processed by Imperial College Atmospheric Physics Group. Every half an hour, a new image is received and stacked electronically on top of the previous image. The stack is like a deck of cards that can be flicked through to show a movie of the very recent weather. We could choose to look at reflected sunlight from our planet to the satellite, but since there is no sunlight at night and we want a continuous movie, we choose to look at the heat radiated from the planet. We remotely sense the infrared. So really here we are looking at a thermal map, where white means cold and black means hot. Grey is a temperature somewhere in between. The high ice clouds show white, the low Earth surface shows grey-black. So we can see straight away that temperature is warmest at the Earth's surface and falls off with height. The movement of the clouds shows the motions of the atmosphere. All this satellite information is added to that gained every hour from all other sources, from a worldwide network of observations. These are all seen together, synoptic observations, and exchanged across the global telecommunications network and fed into the computer. The computer is programmed with instructions, equations that mathematically describe the known laws of physics. This, in other words, is our model. At phenomenal speed, the computer accesses the data at every grid point and solves the equations. To find out how we turn these figures into a forecast, I spoke to Colin Flood at the Met Office headquarters, Bracknell.
Well, we've produced our state of the atmosphere with numbers representing all the different weather elements, and we take that forward by a series of equations. We have a lot of equations which tell us how the atmosphere behaves. These equations tell us how air moves, what happens to the transfer of heat. It's based on how things move, physics, mathematics. So we have a series of equations which we have to solve, and we solve those using our computer, and we take the atmosphere forward in little steps of quarter of an hour. So we start with all our initial conditions that we worked out from the observations, and then we forecast in little hops of quarter of an hour, gradually to take us forward right out to 6 days.
Why such little hops? Why not bigger hops?
Well, the bigger the hops, the bigger the errors we make. If we take little steps and make sure each step is right, then that's the way that reduces the errors, which inevitably do grow in the forecast nevertheless. Well, the errors in the forecast are partly errors in the observations. We haven't got a complete coverage of the whole of the atmosphere. There are places in the atmosphere where we don't know exactly what's happening, so that's one source of error. And the other is in the errors that grow during the forecast process, because that also isn't precise and accurate.
The equations are not precise and accurate.
The equations
or the solutions
are accurate, but it's the solutions of those equations on the grid of points does introduce small errors which gradually grow, and at the moment they grow so that by 10 days we're beginning to lose confidence in the forecast.
Is it possible to reduce your grid spacing, the number of observations that you start with increasing, so there's a tighter and tighter net? Would that help?
Yeah, the closer the net, the more accurate the forecast. That's the fundamental rule governing the accuracy of forecasts. The closer we can get the points together in our computer models, the more accurate the answers. But the disadvantage of that is that the more points we have, the longer it takes to run on the computer. And we already have the fastest computers in the world working on these problems, and we're always looking ahead to the next generation of computers, which will be perhaps 10 times faster and enable us to do the job that bit better.
So, after collecting millions of pieces of special information, employing massive resources, we know what the weather is doing all over the globe. And with our computer model, we can at last make an accurate prediction. Accurate, but not precise. To be precise, to be very specific to a local area, the weatherman must make some mental adjustments to include small local features that the satellites etc. cannot see. For instance, down at the seaside.
One of the nice things about the seaside is that in the afternoon, in the heat of the sun in high summer, you get a sea breeze, or often you do. But it does depend on the air above the land and sea being quite unstable, temperature dropping more than 2 degrees per 1,000 feet, so the hot thermals inland can readily rise, forming a few bubbly clouds. There's more up motion than down motion between the clouds, and the wind, the sea breeze, is the air that's coming in to take the place of the hot air rising, and it brings relief to the beaches, drops the temperature by 3 or 4 degrees.
With these local adjustments, you have your local weather forecast. You will now see just how massive and complex the forecasting operation is. Tracking millions of constantly changing elements, all interacting and affecting each other. Applying science to chaos, meteorologists are trying to predict the unpredictable. And what about the long-term forecast for the climate? We are now just beginning to realize that since the 1950s, we have unwittingly been conducting an experiment with the atmosphere of our planet. More people has meant more growth, more energy, more food, more contamination of the weather machine, the atmosphere. The most serious regional air pollution is acid rain. Coal-fired power stations and cars release sulfur dioxide and nitric oxides that turn into sulfuric and nitric acid, killing trees and lakes in Scandinavia, North Europe, North America and third world countries. The most serious attack on our ozone shield that wards off lethal ultraviolet sunlight comes from chlorofluorocarbons, CFCs. These chlorine molecules are released by refrigerators, air conditioning plants, aerosol sprays and foam packaging. The most serious contamination of our atmosphere comes from the so-called greenhouse gases. Of these gases, carbon dioxide is the most pervasive. An ever-increasing amount of carbon dioxide, that's CO2, is released by burning wood, coal, oil and natural gas. CO2 is absorbed, taken out of the atmosphere, by sea plankton and by forests which we are destroying at an alarming rate. Some of the most important research into the greenhouse effect is being done by Mick Kelly at the Climatic Research Unit at the University of East Anglia.
Greenhouse effect is very important. It preserves life on Earth. We wouldn't be here without it. The carbon dioxide and water vapour that occur naturally in the atmosphere are producing a greenhouse effect already, which is keeping temperatures well above freezing. If it weren't for those gases, then the temperature of the planet would, on average, be below freezing. Now, these gases are significant because they let heat from the sun down through the atmosphere to the Earth's surface, but they won't let heat radiated from the Earth's surface out through the atmosphere back into the space. So more greenhouse gases means that there's more energy trapped near the Earth's surface and the temperature of the planet warms, rises.
And that's the temperature of the air at the surface?
It's the air at the surface and also the ground. As temperatures rise, the glaciers on land melt, as ocean waters warm up, they expand, and both of these factors are likely to produce a rise in sea level, perhaps by as much as a metre in the next 40 years. That's an extreme projection, but it could happen. A metre rise in sea level would inundate a large amount of low-lying land in coastal regions, and 3 billion people live around coastal zones.
I'm walking on the sea defences of the East Anglian coast. This separates that, the salt water, from that, the fresh water. In 1953 they joined together. A storm surged down the North Sea, strong northerly winds driving a sea wall all the way down, the plunger effect of the depression, arriving all at the same time as high tide, the whole area deluged. Of course, this will become invaluable in the next century as the greenhouse gases go on increasing, the global warming hots up, the polar ice caps begin to melt, and the sea level wants to rise to come over this wall and join the rivers inland.
Globally, by the middle of the next century, we could see a rise in temperature of the order of 3 or 4 degrees Celsius worldwide. Now, that doesn't seem a lot compared to the change in the weather from day to day, but over the world as a whole, it's a major change in climate on the scale that brought the planet out of the last ice age, in fact. Temperatures only rose by 4 degrees or so when the ice sheets retreated some 10,000 years ago. So that's the major effect. But we'll also see a much greater rise in temperature at the poles, the sensitive areas, and we'll see climatic zones expanding towards the poles away from the equator. And that'll mean a major change in the weather. If you consider the situation where the North American harvests are reduced and so there's no surplus available worldwide to provide food for people in the Third World suffering harvest failure, either in the form of trade or aid, then it could be absolutely catastrophic. And this is a development that could hit very soon, because it would only take 3 or 4 years drought, successive years of drought in North America to deplete world grain reserves almost to the point of zero. And once we reach that point, then harvest failure anywhere in the world is going to have catastrophic effects.
Catastrophes have hit the planet before. This time, through education, we may well see one coming in time to do something about it. To be forewarned is to be forearmed. Forecasting has become more than just tomorrow's weather. It is touching on all our lives as meteorologists predict massive changes in our climate, changes which are already influencing world politics. More and more extreme weather events simply focuses more and more attention on world climate. I wonder what new weather extremes I'll be forecasting as we begin the countdown to the next century, as our present climate fades.